In this video, we are going to discuss the so-called Gibbs phenomenon, which is a phenomenon that arises while studying Fourier series. Let's give an example first. So if we have a function of this kind, it is a constant in some interval, then we have a discontinuity and the function then becomes negative like this. So there is a discontinuity at this point. Well, what happens is that if we want to represent this function by using a Fourier series, and it means that basically this function is periodically repeated in some kind of interval, so the function repeats periodically like this, and so on and so forth, at the points of discontinuity, so here, 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 the Fourier series representation will showcase a so-called overshoot. So the function will be approximated by using sinusoids, and here in the neighborhood of the point x equals 0 in this case, what happens is that here there is an overshoot. Maybe I can change the thickness of my pen, so let me try like this. The function will behave like this, and then it will approximate our constant in this interval here. So depending on the number of harmonics that we choose for the Fourier series, and it means that we are truncating our Fourier series, because in order to make computations we need to truncate the series. But we can also reason in the limit. So as the number of harmonics increases, the approximation with the Fourier series will become better and better inside this interval here. So you will see less oscillations here. The oscillations will become smaller and smaller, and in the limit the function will coincide with the Fourier series here, but there is still an overshoot very close to the discontinuity here in the limit, and the same holds for the negative values here. So there is an undershoot in this case, a negative overshoot if you want, here as well, and similarly for these discontinuities here. Okay, so we will prove this mathematically, and then I will also show you with Matlab how this kind of overshoot arises. Now let's start. Let's consider a function of this kind. This is actually quite a general phenomenon, so it doesn't really take into account a special form, a special function like this one. It occurs also for other functions whenever there is a discontinuity like this, a jump, and we will consider, without any loss of generality, a function of this kind. The function will be equal to pi over 4 if x belongs to the interval 0, pi, and it will be minus pi over 4 if x belongs to the interval pi, 2 pi. Now, I'm excluding 0 and 2 pi and also pi because it is exactly where there is a jump. So at 0 there is a jump, at pi there is a jump, and at 2 pi there is another jump. So I'm considering this interval here from 0 to 2 pi. So this is 0, this is pi, this is 2 pi here. The function here is equal to pi over 4, whereas in here it is minus pi over 4. Now if we want to represent the function with a Fourier series, the function f of x can be written as, so this equal sign is an equal sign almost everywhere except in the neighborhood of these discontinuities. So this is how we should interpret this equal sign. And the Fourier series can be written as a0 over 2 plus sum with the index n going from 1 to infinity. We have a sub n cosine of 2 pi n divided by the period of the function, that in general is equal to L, but in this case L is equal to 2 pi. So this formula will simplify. X plus bn sine of 2 pi n x over L. And The coefficients can be calculated like this. A sub n is equal to 2 over L integral from 0 to L f of x cosine of 2 pi n over Lx dx for n greater than or equal to 1. A0 is 2 over L integral from 0 to L f of x dx. So in principle, you can use this formula also for A0. If you set n equal to 0, this formula also works. But usually we make a distinction between the index n equal to 0 and n greater than or equal to 1. Similarly, Bn is equal to 2 over L integral from 0 to L f of x sine of 2 pi n over Lx dx. Now, we can calculate these coefficients by considering the fact that the function can be expressed in this way. So A sub n will be equal to 2 over 2 pi, so L is equal to 2 pi, so we can write 1 over pi integral from 0 to pi. So in this case, L is equal to 2 pi, but we can split the integral between 0 pi and pi to pi, because f of x is equal to pi over 4 if x is between 0 and pi, so we can put pi over 4 here, cosine of nx dx, and then we get minus 1 over pi, integral from pi to 2 pi, pi over 4, cosine of nx dx. Now it's very easy to calculate these integrals. They will yield 0. And a0 is also equal to 0 if we do the calculation, whereas bn, after a simple calculation, you get 1 over 2n, 1 minus 1 to the n, like this. So you can write the Fourier series f of x is equal to summation with the index n going from 1 to infinity, and then you get 1 over n, 1 minus 1 to the n, divided by 2 sine of nx, like this. And this means that if you consider some terms, you have for n equal 1 you get sine of x, then for n equal to 2 you get 0 because this will give you 0. For n equal to 3 you will get 1 over 3 sine of 3x. For n equal to 4 you get 0, then you get 1 over 5 sine of 5x, and you get the pattern here. It's a very easy pattern. Now, what we are going to consider is partial sums, because the Fourier series is a series, so it means that we are summing an infinite number of terms. But in general, by using calculators, we cannot calculate the Fourier series. We can only sum a finite number of these harmonics, so we can get an approximation of the series. And this is basically what we are going to do now. We are going to make some considerations by assuming that this series here will be truncated. So let's consider partial sums for some integer capital N. And let's call the function f sub n of x. Now, this will be sine of x plus 1 over 3 sine of 3x plus dot 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 plus 1 over n minus 1 sine of n minus 1 times x. Here I'm implicitly assuming that n is an even number. Why? Well, because you can see that we are summing n over 2 terms here. These are n over 2 because we have sine of x, which corresponds to the argument where we have 1 times x. Then we get 3 from here, then we get 5, then we get 7, all the way up to n minus 1 here. And how many terms do I have? Well, if I also consider the following terms, 2, 4, 6, 8, dot, 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 and then we get n, these two here are, of course, n terms, right? If we consider all these terms, then that will equal n terms. But this number of terms is exactly coincident with this number of terms, right? Because 1 corresponds to 2 with a one-to-one correspondence if you want. So 3 corresponds to 4, 5 corresponds to 6, and so on and so forth. So there is a one-to-one correspondence, which means that the number of these terms is coincident with the number of these terms. But 2, 4, 6, 8, all the way up to n, how many terms do we have? Well, we get n over 2 terms. So this will be n over 2, and this will be n over 2 as well. This means that this will have to be odd, whereas this will have to be even. But the fact that n is an even number is not important. You can also consider an odd number, and then you can make similar considerations. There is no problem with that. Now let me cancel this. This is not very important. I will cancel all of this. Now let's calculate what is the value f sub n of 0. Well, it's very easy. It is equal to 0 because when you set x equal to 0, all these signs will go to 0. And this value can also be written as minus pi over 4 plus pi over 4 divided by 2, which is simply equal to f of 0 minus plus f of 0 plus divided by 2. So it is the average of the initial function f of x, and you can consider this function to be periodic. So here I defined it only in the interval 0 to pi, but you have to think that this function repeats periodically over the real line. It will also be defined for negative values of x, and for x slightly greater than 0 it will be pi over 4, whereas for x slightly negative, so slightly less than 0, it will be minus pi over 4. But this function is not defined at x equal to 0, so there is a discontinuity there, there is a jump. Whereas the Fourier series, actually this is not the Fourier series, it is truncated, but even if n goes to infinity, so when n goes to infinity, this is the Fourier series, it will still be equal to 0. So even if the function is not defined at x equal to 0, we get a value for the Fourier series at x equal to 0, which in general is equal to the average of the function evaluated at 0 minus and 0 plus. So it is some kind of average, as you can see. Now, I don't want to stop here. More can be said about the neighborhood of the point x equal to 0. Let's consider f sub n of the period of the function divided by 2n, where n in general can be very large. So I'm considering this value, and then we will let n go to infinity. When n goes to infinity, this value here will be slightly greater than 0. So it means that we will calculate f sub n at 0 plus. But L is equal to 2 pi, so this is equal to f sub n of 2 pi over 2n. And by considering the definition of f sub n, this will be equal to sine of pi over n plus 1 over 3 sine of 3 pi over n, because of course 2 pi over 2n is equal to pi over n, plus dot 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 plus 1 over n minus 1, and then we get n minus 1 times pi over n, like this. And now let me rearrange these terms. I will rewrite this expression like this. So I will multiply it by pi over n. So I will also have to divide by pi over n. So I have sine of pi over n divided by pi over n plus sine of 3 pi over n divided by 3 pi over n, because here we also have a factor of 3, plus dot 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 plus sine of n minus 1 pi over n divided by n minus 1 times pi over n. Now, I'm almost done, but let's do one more thing. Here I will multiply by 2, and of course I will have to divide by 2 as well. So why did I multiply by 2? This is actually quite important because we will let n go to infinity. And if you think about it, when n goes to infinity, all these summations, all these terms will be close to each other because n is very large and therefore this argument of the sign will be very small. This will be very small. Then here we are going to increase the argument of the sign by 2 pi over n. So if we add 2 pi over n to pi over n, we get 3 pi over n. So the increment that we have from here to here is simply 2 pi over n. Then similarly, when we go to 3 pi over n to 5 pi over n, we have another increment by 2 pi over n, and so on and so forth. So the increment from one term to the other is 2 pi over n, which is also here. And if you think about it, when n goes to infinity, this can be written as an integral. This will be equal to 1 over 2 as n goes to infinity times the integral of the function sine of x over x dx. In this case, dx coincides with 2 pi over n in the limit, whereas x will replace these arguments in general, and we will have to sum from x equal to 0, because when n goes to infinity, you can see that this will go to 0, this will go to 0 as well. So we start at x equal to 0, 0 plus if you want, because x equal to 0 is a discontinuity in general, because we have x in the denominator. But if you think about it, even x equal to 0 is not problematic. It is not troublesome, because in the limit, sine of x over x will give me 1, right? So x equal to 0 is a discontinuity that can be removed. So we don't have to think too much about x equal to 0. Whereas, if you take a look at this last term, when n goes to infinity, this argument will go to pi, as well as this one. So we have to integrate from 0 to pi, like this. What we get from here is basically this. The limit, as n goes to infinity, of f sub n of 2 pi divided by 2n, or if you want, you just have pi over n here, is equal to, in the limit, 1/2 integral from 0 to pi sine of x over x dx. Now, for convenience, this can be rewritten in this form: pi over 4 plus pi over 2 times 1 over pi integral from 0 to pi sine of x dx over x. And then we also get minus 1 over 2. If you check, this equality is trivially satisfied. It is very basic math from here to here. And similarly, we can also calculate the limit as n goes to infinity of f sub n of minus pi over n. And in this case, it is quite easy to convince oneself that this is equal to minus 1 over 2 integral from 0 to pi sine of x over x dx, and it can be easily motivated from here. You can see that if you change the argument to minus pi over n here to minus 3 pi over n, since the sign is an odd function, you will get a minus sign here. And so it's quite a trivial result. And similarly, this one can be manipulated like this. So this can be written as minus pi over 4 minus pi over 2. And then here you get 1 over pi integral from 0 to pi sine of x over x dx. minus 1 over 2. And this is quite important because you can see that when n goes to infinity, the Fourier series, now we can talk about Fourier series because if n goes to infinity, this will be a series. And this argument will approach 0 plus, so 0 from the right. This will be equal to pi over 4, and pi over 4 is simply equal to f of 0 plus. So it is exactly our function on the right of x equal to 0. Whereas here, pi over 2, if you think about it, it is equal to the jump that we have, because we go from minus pi over 4 to pi over 4 here. So the jump, this jump here, will be pi over 2. And then this jump is multiplied by a number, because this is just a number. And we have the same number here and here. This number is approximately equal to 0.0895. So basically this is just, in the limit, it is 9% of the jump, right? Because we have the jump multiplied by this percentage here, 9% of the jump. Whereas from the left, the series calculated at 0 minus, so this will be 0 minus when n goes to infinity. This is just f of 0 minus, and then here we have minus the jump multiplied by the same number. So basically what this means, if we consider our function, it means that even in the limit, in the neighborhood of the point x equal to 0, at the point x equal to 0, the function will be 0. Whereas very close to this point, but on the right, the function will have an overshoot here. Then, of course, the greater the number of harmonics that we use, the better this approximation. So the only difference is very close to the point x equal to 0. Here we have an overshoot, whereas here we have an undershoot here, which is quite difficult to draw precisely, but we will see that more accurately with Matlab, so we will do a simulation. And the fact that we have an overshoot on the right is due to the fact that we have f of 0 plus another quantity which is 9% of the jump. So we can quantify this kind of overshoot. And we can also quantify the undershoot here. So we have a minus in this case. We have f of 0 minus the jump times a positive quantity here. So that's why we have an undershoot like this. Here we go below this level, which is minus pi over 4. Whereas here on the right, we go upwards of pi over 4. So this will be greater than pi over 4. Now let's go to Matlab. Let's take a look at Matlab. I have prepared a script here, which is a very easy script. So I start by setting the number of harmonics here. So for example, we can start with 10 harmonics. So n equal to 10. Then I define an interval from minus pi to pi. And then here I calculate the function f sub n in this case. So we are summing all the harmonics. We first set f equal to 0 and then we sum the harmonics like this. So I am considering this formula here, but I'm truncating this series at lowercase n equal to capital N. So here instead of infinity, of course, I will have to truncate it to some number capital N. And then here I simply plot the function. And after I plot the function, I calculate the integral that I showed you earlier. So this integral here can be evaluated numerically. this integral here. Then I can evaluate this number here, so it's 1 over pi integral from 0 to pi sine of x over x dx minus 1/2. That is just a number, and I calculate it here. Then I can calculate the right overshoot and also the left overshoot. So with these two formulas here, this will be the overshoot that I have on the right, whereas this will be the overshoot that I have on the left, very close to the point x equal to 0. And here basically I also plot the theoretical overshoot like this. So I calculate these values and I plot them in the same graph that I plot in here. So let's first start with 10 harmonics. Here you can see that the function has the following form. This is the overshoot. The theoretical overshoot is not exactly coincident with the function itself. So in this case, I have plotted the theoretical overshoot near the maximum of the function. So the maximum that I have near x equal to 0. We know that the theoretical overshoot in general should be very, very close to x equal to 0. So in this case, I didn't plot it here because otherwise I could not make a comparison between the maximum of the function and the theoretical overshoot. As we increase the number of harmonics, we expect that this theoretical overshoot will get closer and closer to the point x equal to 0, so to the vertical line here, the vertical axis, the y-axis, whatever you want to call it. Now let's calculate the same truncated series when n is equal to 100. So we increase the number of harmonics, and you can see now that the approximation is better. The function here will oscillate around the value pi over 4. So here we have some kind of a sinusoidal function that will oscillate around pi over 4. And pi over 4 is approximately 0.785. So it's quite an accurate approximation. You can see the overshoot, which is getting closer to the point x equal to 0. And then if we increase the number of harmonics to 1000, this is what we get. You can see that near x equal to 0 we still get an overshoot, and this overshoot is getting closer to x equal to 0. And here in this interval you can see that the approximation gets better and better. Of course, if you enlarge the plot, you can still see an oscillatory behavior, but these oscillations here are way smaller than before. You can see that they oscillate between two very close points. You can see that it oscillates between 0.7848 and 0.7860. So the oscillations are very close to each other. And you can increase, in principle, the number of harmonics by whatever number you want. So let's do 10,000. In this case, it will take longer to make this calculation because there are a lot of harmonics and Matlab will take more time to show me the result. But here it is. Now here you can see that this function is getting closer and closer to the function that we approximated, namely this function here, which repeats periodically. So I'm talking about this. And the overshoot now is very, very close to the point x equal to 0. You can see that we are very close to x equal to 0 because this is 3.5 times 10 to the minus 4 on the x-axis. Whereas the oscillations are very, very small now in this region. And you can see that. We can conclude that as n goes to infinity, the function will be approximated perfectly by the Fourier series, but at the same time, near the point x equal to 0, we still have an overshoot. This will not be eliminated even if n goes to infinity. So that's the interesting aspect of Fourier series. And the function will be equal to 0 when x equal to 0. So we also know that the function will have a value here at x equal to 0, the Fourier series representation of the function, whereas the function itself might not have a value at x equal to 0. And in principle, there could be a discontinuity and the function may not be defined at x equal to 0, but the Fourier series is still defined at x equal to 0. This is a key aspect of the Fourier series.